Okay, well, let me start thanking the organizers for this very kind invitation. It's my great pleasure to be here again in front of you and giving a talk at this ICFO-IMPRS joint workshop. So for me, it's a special occasion like the previous one, because I mean, on the one hand, I'm in IMPRS and I'm part of IMPRS, and I was also one of the initiators. And on the other hand, I am also, in a sense, part of ICFO. So, I mean, I know ICFO from the very beginning, and I have been participating in many discussions and many committees and many organizations there. So these are like the two parts in my soul that now join together for this workshop. So it's a pleasure to give a talk here. Okay, so I'm going to give a talk about quantum computers and many-body problems. So this is going to be relatively simple. For most of it, at some point it will get a little bit technical, but if you find it technical, just simple disconnect for that time and then reconnect again, because then it will go back to something that is not technical. Anyway, so let me just start with this kind of vision of a quantum computers that all of us had in mind already for many years. In my case, it's more than 25 years. It would be a device that it's based on the laws of quantum physics, and in which just operating quantum bits, qubits, with the loss of quantum bits of quantum physics just by quantum gates, then you should be able to solve some problems that are difficult to be solved with standard computers. In particular, you can speed up the solution of some problems, and we know by now actually a big bunch of problems that would benefit very much from such a quantum computer. There is a lot of excitement nowadays in the field, and because finally there has been already some quantum computers built that have already had solved some task in a way that we cannot solve with classical computers. And in particular, these are two kinds of computers that one of them we call analog quantum computers, and the other one are noise intermediate scale quantum devices. So they are not the quantum computers that we always imagine. They are not the same as these quantum computers, because when some of them work in an analog way, not in a digital way, and actually both of them have errors, and so they are not perfect. So if we want to use now the algorithms that were developed for quantum computers in those devices, then typically they will not work. And so all the promises that were held in the past will not be fulfilled, at least until we don't have one scalable quantum computer. However, with both systems, analog quantum computers and these devices, there have been claims during the last 5 years or so that people have solved problems that we cannot solve with classical computers. And so that's a good question that I think that has popped up to the minds of many people working on quantum information is, can we develop algorithms that would work also for these not noisy computers, for these non-perfect computers, and in which one could hope, or even maybe one can prove some kind of acceleration. And apart from that, we would like that these problems have certain interest. As you know, the paradigmatic example that Google solved 2 years ago is fantastic. It proves really quantum advantage. So they solve, or they do something that we cannot do with classical computers. However, it's a purely academic problem. It's a problem that it's not useful for anything that we know. And it's very doubtful that any problem of that kind would be useful for anything. That's why there is now a big race in trying to see whether these analog quantum computers or these NIST devices could be useful for something. And we hear actually even in newspapers that people claim that they have found algorithms. However, I mean, some of them are very heuristic, and I mean, there is not so much evidence behind that. So what I wanted to show in this talk is that actually there is a hope for analog quantum computers, NIST devices, but also for digital, the future quantum computers, to solve problems, some certain kind of problems. And these are related to many-body physics. So these are problems that appear in science especially, but some of them are also related to the industry, but mostly in science. And so they are related, for example, to high energy physics. So solving, let's say, the equations of the standard model in predicting, well, what are the mass of different particles, what are the phases of matter under certain conditions and certain temperature, certain chemical potential, and so on. Or they relate to condensed matter physics. So we would like to know what happens when we have a solid, for example, in which particles are interacting with each other strongly and obeying the rules of quantum physics, that we know that under these conditions, then we can have very exotic behavior. And this exotic behavior is very hard to describe with classical computers. Or in chemistry, in which one would like to solve what are, for example, the geometrical configuration of certain molecules, or if certain reactions would take place, or how to accelerate certain reactions. All these problems in chemistry, condensed matter physics, and high energy physics share the same question behind, and namely that they are very hard to solve them with classical computers. And let me just explain you why. And so for that, what you do in each of these systems is, first of all, you want to solve them with a classical computer, then you have to discretize space, not classical computer nor quantum computer. I mean, it would work with a continuous space, or you discretize space. So this means that you put the problem on a lattice. So you make something which is here in a kind of cartoon picture represented here. So you discretize a space, and each point of this lattice is one represents a point in space. And then you just write the problem in space according to this lattice. So typically, so you're dealing with electrons maybe moving in a solid, then what you will have is that the electrons in the model will be hopping between the different lattice sites. Or if you're studying magnetic properties of material that are described in terms of the spins of the particles that are making up this material, then you would put one of these spins at each of these lattice sites. And the same with any other of these systems. At the end, you have a model on a lattice, and then the fundamental equations will tell you what is the Hamiltonian that describes interactions in this lattice. So this is a model to solve the problems that they are real problems that you want to solve. And so the question is, if we want to solve this model with a classical computer, if we want to make predictions about this model, so for example, how it will evolve, it will become magnetic in the future, will be superconducting, will not be superconducting, what will be some other electrical or magnetic properties, maybe what are the masses of the excitations, the particles, and so on. Then we typically have to solve a many-body problem, because there are like many lattice sites here. And this, if we want to solve it in the context of quantum physics, then we typically will have to write the wave functions that corresponds to the physical situations that we are studying. So whatever you studied, the zero temperature behavior of this system, or the dynamics of the system, then you will have to write what is the quantum state. You want to describe the physical properties of the system. And even in the simplest case, in which this model here would be made out of the simplest quantum particles, namely spin 1/2 particles or qubits, then the state that you will have to write will be a linear superposition of all possible configurations, running from the configurations with all the spins are down, all the way up to all the spins being up. And if you count the number of possible configurations, there are 2 to the power n configurations. So therefore, we will have to describe states which are linear combinations, linear superpositions of 2 to the power n configurations. And these coefficients that are in front will tell us what are the physical properties, will describe all the physical properties of that system. So if we want to make any prediction, or we want to describe any physical property, then we'll typically will have to compute what are these complex coefficients. And since there are as many complex coefficients as configurations, then we will have to use a memory in our quantum computer that should be able to store 2 to the power n coefficients. And therefore, the memory will have to grow exponentially with the number of qubits that we have here. And the number of qubits is, I mean, proportional basically to the volume that where we are studying in these problems or is related also to the number of electrons maybe that we have in a molecule. So you see that the memory of our classical computers grows exponentially with the number of qubits that we want to simulate. But not only that, if we want to compute anything, we will have to do at least one operation with each of the coefficients. And since we have 2 to the power n coefficients, this means that we'll have to do at least 2 to the power n operations. So the computational time will also be exponential in n. So we have a very bizarre situation in computation. In computational physics is not only that the time to solve a problem requires an exponential, grows exponentially with the number of subsystems that we have, but also the memory. So remind you that many times in computer science, you have problems like optimization problems in which the time grows exponentially with the number of, let's say, let's say towns that you want to sort, for example, in a traveling salesman. But here is not only in quantum problems, apart from this exponential time growth that you have, you are also confronted to the fact that you have an exponential memory growth. So they are both together. And this makes these problems even much more difficult than typically problems that are difficult, let's say, in computer science. In fact, one could try to say, what happens if we trade a memory by time? So imagine that you say, well, I have a memory that can only grow linearly with the size of the system, or it can only have some fixed amount. So for example, imagine that you say, well, I cannot have a memory that is larger than the number of atoms that we have on the planet Earth, because I will never be able to make such a big computer. Then this puts a limitation on the size of the memory that you can have. And the question is whether you would be able still with that computer to solve problems, many-body problems, and indeed, this is possible, but now you have to pay a price in the time. The fact that you have limited resources in memories means that you have to pay extra resources in time. And these extra resources in time means that typically, I mean, for these problems, I don't want to discuss it here, but it grows super exponential now with the number. This 2 to the n to the power n is a super exponential growing with the number of subsystems. So you see, you want to now compare the difficulty of quantum problems, let's say, with classical problems, then it's not only exponential in time, but this is even super exponential in time, because you have to treat memory on equal footing. And if you do that, this will give you a huge overhead. So that's why quantum many-body problems are very difficult for classical computers. Of course, there are many approximate methods and so on, but they work under some restricted conditions. And here I'm talking about solving all these general problems. In fact, that's something that is not new. That's something that was very well understood by many people, and in particular, Richard Feynman understood that in the 80s, 30 or 40 years ago. And so he realized that actually, at least the part in memory, this exponential scale that we have in memory could be saved if we would use quantum systems instead of classical computers. If we would use quantum computers. In fact, he coined in his paper, his famous paper, the word quantum simulation and quantum computation. And what he says is that if we solve a problem, in his case, he was concerned problems in high energy physics, because at that time, I mean, lattice gauge theories appeared, and so people, realized that one could solve standard models. The standard model, which was very fashionable at that moment, yes, if one had a computer that could solve lattice problems, but right away they found this problem that I mentioned here in solving with classical computer. And he says, well, the problem is that actually we are trying to use classical system to store quantum states, or classical bits if we want to store quantum bits. So if we would use quantum bits, and we'll have a quantum computer not made out of bits but of qubits, then we will save the memory. And so if we want to now have a model with that, describe a model that has n qubits, instead of having to use 2 to the power n bits, we will have to use only n qubits in our quantum computer. So that's a linear dependence on the memory. And this automatically gives you a gain with respect to classical computers. And so that's, of course, that's true. And that's a real advantage that comes right away without thinking about that in quantum computers. If you want to solve quantum many-body problems, then right away, then you gain in memory. So the question that remains open is what happens with time? So do you also gain in time or not? And so that's something that, it's worth investigating. So now you have algorithms to solve the problems that I told you before. You solve them with a quantum computer. What would be the time requirements? So the time may grow like n, like the number of qubits, which would be great because this would mean that we could simulate this very well. However, if it grows exponentially, this will also put some restrictions on how we can use quantum computers to solve quantum many-body problems. Particularly, if we have an exponential scaling like that, then typically I will not be able to go with quantum computers beyond 50 qubits or 100 qubits or something of that sort. And so this is what I want to talk about. So now with quantum computers, and in particular with these first generations of quantum computers and these devices, so with the algorithms that we have, and maybe with new algorithms, how long does it take to solve the interesting problems for physics or chemistry? Okay, and so again, I will consider lattice problems. So I will consider that I have certain number of particles. This could be qubits, this could be qubits, this could even be fermions, but I will not deal with that here, or even bosons. So, but most of the things that I'm saying will be valid for fermions and bosons as well. However, I will deal here with qubits, which is the simplest case. And I will consider, like I told you at the beginning, that, because based on basic principles, then we know what is the Hamiltonian. So somebody gives you some geometric configuration, like for example, this one here, where there are two kinds of qubits, the green qubits and the red qubits, but it could be a different one, could be a different lattice, can be a lattice in 3 dimensions, can be a lattice that has Emilian geometry, and gives us a Hamiltonian that tells us how these particles interact with each other. And then I'm interested in solving the following question. So first of all, the dynamics. So I would like to know what happens if I start with some initial state, and then I let it evolve according to this Hamiltonian. So as you know, the Hamiltonian in physics plays 2 roles. Okay, so that's something that when we study quantum physics, then we study them separately, and we never, sometimes we don't connect them, but actually the Hamiltonians in physics play completely different roles. On the one hand, they generate the dynamics, so through Schrodinger equation that tell us how the wave function will grow. And so this is the first kind of problems that I'm interested in, the dynamics. So I start with some initial state, and then I evolve with my Hamiltonian, and I would like to know what are the physical properties of my system after a certain time. Okay, for example, I would like to start with some spins that are depolarized, and then I put my Hamiltonian, and maybe at some point they polarize in some particular way, there is some magnetization, or there are some correlations created, and this is what I would like to learn. The second and third problem are related to the other use of Hamiltonians. In quantum physics, Hamiltonians not only tell us about the dynamics, but also tell us about equilibrium through the postulates of quantum statistical mechanics. It tells us that if our system would be in equilibrium with a reservoir and we let it for a while, then at some point, if the interaction with the reservoir are sufficiently slow, then the system will thermalize. And thermalize means that the state will be described in terms of something that depends on the Hamiltonian. In fact, it will be described in terms of what is called a Gibbs state. Rho, the density matrix, will be exponential of minus beta times h, where beta is 1 divided by the temperature. So this is what I would like to study. Now, not dynamics, but equilibrium. So what happens if my system is in equilibrium, and therefore, if I have equilibrium, I can talk about the temperature. And I would like to know what happens as a function of the temperature. What happens if my system is in equilibrium? What are the physical properties if I'm at 0 temperature or I'm at a finite temperature? And that's what I'll describe here. So quantum algorithms for these problems, and I would like to know if I had one of these quantum computers, how long it will take to solve these problems as a function of the size of my system. And I would like to know also if I will be able to run these problems with analog quantum simulators or with these devices which are noisy. And these are the sort of questions that I will pose during my talk. And during the last part of my talk, I will talk about some possible applications and some particular problems on quantum simulations, on condensed matter physics, high energy physics, and quantum chemistry. And I will give you an overview of what is the situation in analog simulation with those systems. Okay, so then I start with the first part of my talk. At the beginning would be very descriptive, and it will get technical when I talk about finite temperature. And then I'll go to some of these applications. Okay, so let's go to quantum algorithms, and let's go problem by problem to the ones that I mentioned before. So the first problem was about dynamics. So you have in the right corner here, again, the problem. Somebody gives me this lattice with some qubits and some Hamiltonians. And most of the time, I forgot to say that, I will consider that these Hamiltonians are local. Okay, so this is what is represented here. You see that the Hamiltonian maybe involve the interaction of these 5 qubits that are in some particular region of states, but they are not long-range interactions, just maybe related to very short-range interactions. So I typically will not use it so much. I will use the fact that the problem, these are few body interactions, but I don't want to get technical. So I think that this simply, you consider now, restrict yourselves to interactions that are local, okay, so that they interact only in some region of space. And if you push me very much and you say that this is not realistic because there are systems where the interactions are not local, I will tell you that any fundamental theory has to be local. Okay, so you go to the standard model is local because otherwise you would not respect causality. Even if you have electrons interacting with each other, you would say that the Coulomb interaction decays like a power law, like 1 divided by R, and that's not local, but actually this is not true because the electrons interact mediated by photons. So the fundamental theory that describes the interaction of electron is not Coulomb interaction, it's quantum electrodynamics. And in quantum electrodynamics, you include the electrons and you include the field, then all the interactions are local. However, of course, when you describe effective theories in which you just eliminate the electromagnetic field, then of course you get something that is non-local. But if you would have a problem that is non-local, you can always rewrite the fundamental theory, it would be local, put it on a lattice, solve it, and this would be a local Hamiltonian. So with that, I'm saying that by restricting myself to local Hamiltonians, I mean, in principle, even though in practice, of course, might be not so useful, in principle, that's not such a big restriction. And that's the problem, how it's a little bit more mathematically formulated. So I'm giving some initial state. And this state, let me assume that is easy to prepare. So it's, for example, a product state in which each of the qubits is in one state that is easy to prepare. For example, all in 0, all spins down if we have spins or something like that, or maybe up, down, up, down, up, down. So some state that you can easily prepare with your system. And then you would like to know properties about your state after some time. It's not that you would like, and this is, I mean, this is the evolution of the state. So this is the state that would fulfill Schrödinger equation with this Hamiltonian. And the goal is not to know what is the state psi. And because if I want to know what is the state psi, I would like to know what are these coefficients that I mentioned before. And therefore, I would need these exponential resources that we want to avoid. So the point of quantum computation for solving quantum many-body problems is to never compute anything about the wave function, but to compute physical properties. And that's what is represented here. So somebody gives me some observable, and the goal is to compute the expectation value of the observable. Okay, so again, somebody gives me some initial state, gives me the Hamiltonian, and gives me one observable, and my goal is to compute what is the expectation value of this observable after some time. So for example, this observable could be like the magnetization per particle. So I would like to know what is the average magnetization of each of the particles, whether they are spin up or spin down, and I would like to compute the average. Okay, and something like that. And so there is an operator that I have to plug here and compute that. And that's a problem actually that is very difficult with a classical computer. And that's one of the problems that takes an exponential time with a classical computer. So what about a quantum computer? Well, actually, that's basically the first algorithm that appeared in quantum computing was, or one of the first, the first in quantum simulator was by Seth Lloyd, and he showed that actually this problem can be very efficiently be solved with a quantum computer. The idea is that what you would do is that you start with your quantum computer with the initial state psi 0. I said that it's easy to prepare. And then you will use your quantum computer in terms of quantum gates to evolve your system. And so what you do is that you decompose the time in which you want to evolve, the total time where you want to have the solution, where you want to compute your observable, you cut it in small pieces. You also discretize time. And then from one state to the next one, then you apply a quantum computation. And from this one to the next one, you apply a quantum computation. And what Seth Lloyd showed is that indeed it is possible that if we make these small steps and time steps, the evolution given during a small time step by this Hamiltonian can be written in terms of simple gates, very simple gates, local gates. And so you count how many gates you have to perform at the end. Then with this algorithm, the gates scale quadratically with n, the number of qubits that you have in your system, and the simulation time, as well as with the error that you allow, inversely proportional to the error that you allow. So at the end, you would like to compute this expectation value with certain error epsilon. So what you will do is you prepare your state, you apply these gates, and then you will measure this observable. Then you will do it again, you will do it again, you will do it again, you will do it again. And at the end, you take all the outcomes of all your measurements and take the average, and this would be your estimator for this observable. And he showed that this could be done in a time that scales in this way. Actually, this algorithm is not optimal. In the meantime, people have developed much better algorithms than this one. And so the best one that I know takes a time that is not quadratic, but linearly with n, is linearly with time, and scales like logarithm of 1 divided by the error. So that's a wonderful algorithm. So this means that in a quantum computer, and if we had a quantum computer, we could solve dynamical many-body problems in much more efficiently than with classical computers. For classical computers, one can show that the computational time scales like 2 to the n, and this is right. Even so, the whatever you use, you can have an algorithm that would not use exponential resources in memory for that. But anyway, so the first conclusion is that yes, we have quantum algorithms for the dynamics that are very good. However, now these algorithms, first of all, they are not very natural for NISQ devices. And the reason is that in this discretization, so for example, in this one here, then if you want to apply it, then you will have to do many gates. There is an overhead in gates that you have to apply. And, or you think in terms of this discretization in time, since these time steps have to be very small, then you will have to do many gates. And you know that these NISQ devices have errors, so these errors will accumulate and they will not work that well. However, for analog quantum computers, this is straightforward. Actually, what you can do is that to evolve directly. So you will just take your analog quantum simulator. You will engineer the interactions between your qubits in the same way as the one dictated by your Hamiltonian, and then let it evolve. You will not have to do anything actively. And therefore, that's very well suited for analog quantum simulators. However, in these analog quantum simulators are errors, and there is the whole issue here that I'm not addressing. So how these errors accumulate and how they will affect the final result. Or in other words, you want to have some error at the end, epsilon, in your expectation value. So how much error are you allowed in this Hamiltonian? So how perfect has to be your Hamiltonian? And I'm not addressing this now here. People have thought about these things, and we know about some scalings, and I will mention something about that towards the end of my talk. Okay, so now what about the ground state? So let me now change the problem and let's go to an equilibrium problem. So again, I have a Hamiltonian, and now the goal is not to study the dynamics, but to study what will be the physical properties at zero temperature. So again, I want to know physical properties. Somebody gives me an observable, and I would like to compute now expectation values of my observable with one state. But this state now is not the dynamical, but it's just the ground state of my system. That's the state that corresponds to zero temperature. So what I will have to do with a classical computer is to take this Hamiltonian, calculate the eigenstates and eigenvalues, calculate the lowest eigenvalue, the corresponding eigenstate, and do computations with that. And this takes a big effort, as I mentioned before. So what happened if I want to do it now with a quantum computer? Well, it turns out that this problem, in full generality, is difficult for a quantum computer. In fact, you formulate it as a decision problem, like computer scientists formulate problems of that kind. It belongs to the complexity class QMA, that stands for Quantum Merlin-Arthur problems. These are problems for quantum computers that are the equivalent to NP problems for classical computers. So let me just explain you a little bit about these complexity classes. So as you know, decision problems in Computer science are classified depending on what is the time that it requires to solve it, to give a decision, to say yes or no. So there are the problems that take polynomial time. This class P of problems. There are the problems that take more than polynomial time, for example, exponential time with the size of the system. However, they are easy to check with a classical computer, meaning that you know the solution, then you can check indeed that it's a solution in polynomial time with a classical computer. That's this class NP. A problem in P is multiplication. So is the multiplication of two numbers larger than something or smaller than something? It's a decision problem, and then this problem is in P. A problem in NP is the factorization problem. It's very difficult to know if there is a factor smaller than some other one. That's a decision problem. However, if I give you the factor, it's very easy to say that is a factor just by dividing, and that's a problem in NP. And so this class BQP is the class of problems that can be efficiently solved with a quantum computer. So this is like the P, but for quantum computers, and the class QMA is like the class NP for quantum computers. So these are decision problems that can be that are difficult to solve. However, you have a quantum computer, you can check them efficiently with certain probability. Okay, this is what is QMA. And it turns out that this is a problem, this problem of ground state properties is a problem that it's here. So this means that in a quantum computer, in the worst case, it will take an exponential time with them. However, I mean, there's still some room here. Exponential means that it's case like 2 to the power alpha n, but this alpha could be equal to 100, in which case this would make things impossible, or it could be 0.00001, in which it would make things more still feasible for very big systems. So the question is, how much is this alpha? And so now there are many algorithms, and in particular, well, I mean, well, maybe I put it here. So we had an algorithm a couple of years ago, where I think that is the best scaling, which scales like 2 to the power n halves. You take an AIF algorithm, a phase estimation and parameter simplification and so on, it will run at 2 to the power 2n. And so you have to do some effort with your algorithm to reduce this power. Okay, so in this case, like logarithm of 1 over the epsilon, and this is the gap that I don't want to discuss here. In any case, so we have that quantum computers, I mean, still take an exponential time. Still, if we compare with classical computer, with a classical computer for this problem, again, if we restrict the memory, as I mentioned at the beginning, then the time it takes is 2 to the n to the power n. So it's super exponential still, even though it's I mean, it's exponential time is much better than this with a classical computer. However, of course, the fact that you get something like n halves puts some restrictions on how these problems can be solved in practice. So what do we do? So does it mean that we will never be able to use quantum computers to solve zero temperature problems? Well, this is not like that. In fact, I mean, there are some other algorithms. Well, I wanted to mention that this algorithm cannot be applied to NISQ and analog devices because it requires many techniques that are very sophisticated and they don't apply well. So the errors will accumulate very badly in those systems. So the question is that actually, fortunately, there are some other algorithms in which there is a lot of hope. These are called heuristic algorithms. These are algorithms where one cannot prove what is the time that it will take. So it will depend on the problem. So for some problems, it takes a long time. For other problems, maybe fast. And so the question is that it's almost impossible to say beforehand if the problem will take a long time or not a long time. And so the idea here is that, okay, so just try it and that's it. You have your problem. So you have a quantum computer. Let's try this algorithm and maybe it works. And if it works, you're lucky and then it works. And so there are several algorithms, but the most famous ones is this adiabatic algorithm, in which the idea is to change your Hamiltonian from a trivial Hamiltonian to the target Hamiltonian adiabatically to prepare initially the ground state of this initial Hamiltonian, which is a simple Hamiltonian. So for example, one in which there are no interactions, for example, in which there would be like a Hamiltonian that is acting on each of spin independently, which we can solve and prepare the state very easily, and then change adiabatically. And now the question is that indeed the adiabatic theorem tells us that if we change slowly, then the state will always be the ground state of this time-dependent Hamiltonian. And so at the end, we will reach the target Hamiltonian, we will be in the ground state. However, the adiabatic theorem tells us how slowly we have to do. Depends on the problem, how slowly we have to do. And in many cases, the time at which requires to reach this ground state may scale exponentially with the number of qubits. And in that case, I mean, you're, of course, this is not so useful. And so in this case, this adiabatic algorithm will not work. However, for some other cases, we know that this adiabatic algorithms works. And for example, in condensed matter physics, we have a lot of knowledge about problems and how even if you have a critical point, even if your gap closes, that the computational time still will be polynomial even for adiabatic algorithms. So it seems that this adiabatic algorithm will be nevertheless very useful because many problems we are interested in physics, which are not arbitrary problems, there are problems where there are symmetries and so on. For these problems, then the scaling is better. And for adiabatic algorithms, it could be that you can even solve these ground state problems with a polynomial effort in time, not with an exponential, which is the one required for arbitrary problems. So the fact that we are studying some specific kind of problems makes it that maybe this algorithm works very well. However, as I mentioned before, there are many problems for which it's impossible to say beforehand if they will work or not. The second kind of problems are variational algorithms. And these variational algorithms, the idea is they work like classical variational methods. They just prepare with a quantum circuit states, and then you adjust the quantum circuits, the parameters on your quantum circuit in such a way that at the end, when you measure the energy, the observable that you measure is the energy. When you measure the energy, then it's as small as possible. And in that case, then you start changing your coefficients, and at the end you will minimize this energy, and this will be a good guess for your ground state. But nobody tells you that this will be the ground state because many things can happen. First, the variational family, so the circuits that you're using, may not be expressive enough to express the ground state of your system, in which case you will never approach something like that. So maybe always very far away. The other problem is that maybe your let's say your variational wave functions of the circuits are very good. There is some set of parameters which will give you a very good approximation to the ground state, but the question is how to find it. So maybe when you're finding, you're using some gradient methods in which you're trying to minimize the energy as a function of these parameters, but your landscape in energies is very flat and there is no way of finding what the minimum is, or you can be trapped in a local minimum. So actually, and at least our experience with variational algorithm is more like that they're very hard. So at the moment, I have much more hope in adiabatic algorithms than in variational algorithms, but nevertheless, that's very worth exploring because maybe you're lucky, and for some particular class of problems that are very important for industry or whatever, then these variational algorithms would work. However, another advantage that these algorithms have, a very big advantage, is that they can be used both with analog and NIS devices. So nevertheless, nobody promises you that you're going to reach the ground state. Well, if you have a little few errors, so maybe you can approximate still very well. That's a little bit the idea behind it. And that's why there is a big effort, not only to use these adiabatic algorithms, variational algorithms for many body systems, but for many other problems. Okay, so now what I will go, so I'm going very, very slow. So what I will do is to talk a little bit about finite temperature. And I was planning to give you some details about some quantum algorithm that we recently developed. And we is Sirui Lu, who is a master student working in our group, and Mari-Carmen Banyuls, you probably know very well. She's a staff member in our institute. And that we developed this algorithm, and now we are applying this algorithm to different physical systems. And this is done by Sandra Colvinen, Arthur Christianen, and Dominic Wild, together with some experimentalists. And yeah, so as I mentioned, I wanted to give you some highlights about that. So instead of explaining you the algorithm, that will take me some time, I will spend most of the time explaining you what is the problem that we want to solve. And then I will give you a very short hint about the algorithm, and then I will go to the final part of the talk. Okay, so again, it's the same thing as before. So somebody gives us a lattice, gives us a Hamiltonian, and we would like to give an observable, and then we would like to compute now some expectation value. But now this expectation value, we want to do it with respect to some state corresponding to some finite energy. So this means that as before, we take the Hamiltonian and we compute the spectrum, we compute the eigenvalues, and we plot them here, these eigenvalues as a function of the energy. Then, because we will have, these are the eigenvalues, fulfill this equation, then the lowest one, the minimum one, this is the ground state. So that's the one that we were talking before. So when I was saying, okay, let's compute the physical properties of the ground state, what I meant is that you just find the eigenvector corresponding to this eigenvalue and you plug it here and then you compute this quantity. Now we want to do the same thing, but with an other eigenvector, which is here somewhere in the spectrum. So this is what I call finite energy. And so the goal is to do it efficiently. And so let me tell you a couple of things that we know about many-body systems that tell us why this is difficult and what is the physics that is behind that. So imagine that you take one of these Hamiltonians that I gave you, just choose any one that you want. I mean, maybe choose it that is quantum so that it has some operators that don't commute among themselves, but it's local, and then diagonalize. Just take 8 qubits and just plot the eigenvalues. So you will get something like that. So you will find that there are eigenvalues on the sides, like this would be the ground, one corresponding to the ground state, and then when you go towards the center of the spectrum, there are more and more and more, and then there are less and less and less. So this is why sometimes it's very useful in order to express this fact that the eigenvalues appear at the center of the spectrum to talk about density of states. So what we do is that we take some interval of energy, like let's say something like that, and then we count how many eigenstates are there in this interval. Then we move to the right and count how many eigenstates. And then if we do that, then of course, as we go to the center, we will see that there are more and more and more, and there are less. And this is what is called the density of states. Of course, it depends on how do you choose the interval and so on. But what you do is that you increase the number of particles, and now you have 15. Then you have 2 to the power 15 eigenvalues. So you will have a much denser spectrum, of course, because there are many, there is an exponential number of eigenvalues. Right? This is because the Hilbert space grows, I mean, the number of configurations grows exponentially, so the number of eigenvalues is the same as the number of configurations. So this grows, and now you can do the same thing as before. Now it's very difficult to see where there are all the eigenvalues, but you can still plot this density of states, and so you will find that again, it looks very much like that. And actually, you can show very easily that the width of this curve that you have here scales like a square root of n, while the whole spectrum scales like n. That's very simple. That the fact that the spectrum, I mean, runs from something like -n to n, very simple. We have a Hamiltonian. This Hamiltonian is local, so it's acting on the different regions. And so the region surrounding each of the qubits, since we have n qubits, then there are n terms in this Hamiltonian. And each of these terms is of the order, I mean, it's bounded, an operator that is bounded has an energy of the order of 1. So the total maximum energy will be n times this quantity. So this is why this would be n times something, and the minimum will be minus n times something. So that's the width of this will be 2 times n, or some constant times n. However, the width is much smaller, and the width is a square root of n. And I mean, you can easily compute this width. I mean, they give it as an exercise. Think about that, how to compute the width, how to estimate the width of the density of states case, like a square root of n. So you see, if we start increasing and increasing and increasing, then this will get very big, and this width will get very big as well. So that's why typically in condensed matter physics, you work with intensive quantities. You don't talk about the total energy that will scale with n, but you divide by n. You say that what is the energy per latticite, or the energy per particle, and that's what you call the energy density, energy per particle. And now we can do the same plot. So now instead of plotting here E, we plot E divided by n. So what will happen is that our curve is now narrowed, it's smaller, it's divided by n. So it will look like that. And so we can put all the curves now on exactly the same plot. And now what we can do is to increase n, and we will see what we said before, that if we have n equal to 8, this was a square root of n, but now we divide by n because it's per particle. So this means that now as we are increasing and increasing and increasing the size, this is getting very narrow because this increases like 1 divided square root of n again. So this is the square root of n that we had before, divided by n is 1 divided square root of n. So in this scale quantities, now the density of states is getting narrow, 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 and going to a delta function. So we will take here 10,000 particles, you will see just something in the center. So what this means is that all the particles, all the states, or most of the states in a many-body problem are completely in the center of your spectrum. And there are very, very few on the sides. And that's the problem. And that's the problem in many-body physics, that you're working at a finite energy, like what I said before. So you fix the energy density. This is like fixing a line here. And as you increase the number of particles, then you see that you only have access to the tail or the density of states. So you're talking about the property of very few states in your spectrum, and you want to find that. It's like finding, how you call it, a needle in a haystack, right? You have many, many states, and then you start looking for the state that you're looking for, and there is 1 out of 2 to the n, or very few out of 2 to the n, very, very, very few. And that's why this is very difficult to talk about the properties of those states. These are difficult problems in many body physics. And in particular, one particular case is the ground state. In the ground state, you are here just at the border. That's the state, that's the problem that I will mention before. Then there is only one. That's why it's very difficult. But you see that if you're increasing, the situation doesn't seem to be even much better. No? Even if you make an energy that is very close to the center of the spectrum, then will not help so much, because this is very, very narrow as a width 1 divided by n. Okay, but so this is the problem where we can show that actually a quantum computer can help. So that if we have finite energy in some conditions on the energy, that's still difficult for a classical computer because it's this bottleneck. Still, a quantum computer can find those states and can tell you the physical properties of that state. So now, what is the formulation of the problem? Now you have to formulate the problem precisely. And so for that, what you do is the following. So let me take your Hamiltonian H, and we are going to consider H for different n. So we are going to grow the systems and to ask questions on what happens, what is the difficulty of solving this problem if we take bigger and bigger lattices. So what we do is that we fix the energy density. So we fix the small e n, okay, because this is independent of the lattice size. So I give you this energy density and will be valid for all the sizes, right? Because it's the energy per particle. I fix that. And then I say, okay, so fix the energy density, also fix an observable. Okay, so for example, this could be the one that I told you before, the average magnetization, or the expectation value of some observable acting on a signal side, whatever, you fix one. And then what you would like to compute is the expectation value of this observable, and with a state that has this energy. However, this is not sharply formulated, and this is why you want to make statements about how a quantum computer can solve it. This statement that I made, or this formulation, doesn't make sense. The reason is because, you see, if I put some energy here, since this spectrum is discrete, it's very unlikely that there will be an eigenstate exactly at this value. It's actually zero measure. The probability will be zero, right? Because you have a discrete number, you take a continuum point, it's impossible that it coincides with one of the discrete numbers. So this is why this problem is not well formulated, and this is why you have to formulate it in an alternative way. So what you do is that, okay, so I'm not going to talk about the properties of this state here, but I would like to find one state, right, on some distance with respect to this energy, let's say in some interval that is defined by some delta. Okay, so you have to specify also what is the delta that you're allowing. And so what you say is that, actually more formally, that you would like to find a state psi which has these expectation values of the energy that you gave, that is n times the density. And you would like this state that you're taking, maybe not to be precisely an eigenstate, but to have some variance. And these variance you fix beforehand, delta. And also you fix the error in this expectation value. Okay, so again, somebody gives you the Hamiltonian, the kind of problems, somebody gives you the energy density, somebody gives you this observable, and somebody gives you this delta, this variance, and some epsilon, some prescribed precision that you have to achieve with your quantum computer. And the question is, how does the computational time scale with n? And maybe also to see how it scales with epsilon and with delta. So this is the first kind of problems that we would like to solve. The second, okay, so this delta, so how should we choose this delta? I mean, for physical problems, it turns out that this delta should scale like 1 divided by n, or something like that, to have sensitive physical problems. So now you take some specific physical problems and you want to solve using this method, and then you want to have some outcome that is useful for something, that tells you something about the physics, then you better scale this delta with n like 1 divided by n. This is coming from physics, okay? Right. A second kind of problems is in thermal equilibrium. It's not to choose one energy, but actually to take some probability distribution of different energies. So namely, to say that, well, I would like to take an energy E with a probability which follows this Maxwell-Boltzmann law, and then average with respect to all energies. And that's what will happen if we have thermal equilibrium. This is equivalent to computing expectation values with the Gibbs state, which describes thermal equilibrium. So the second problem is not that you fix the energy, but that you fix the temperature. And okay, so the problem now properly formulated is somebody gives you the temperature, somebody gives you the observable, somebody gives you some precision epsilon, and then you would like to compute the expectation value of this observable corresponding to the Gibbs state at this temperature with an error epsilon, and then you're interested in knowing how the computational time scales with n, the number of qubits, but also with epsilon and the temperature. So these are the problems that I want to address. And okay, so what you can do is to check at classical algorithms, how these classical algorithms operate with these problems. And so for the first problem, if you work in 1D, the best existing algorithm I'm aware of is tensor networks, matrix product state. And with matrix product state, you want to compute expectation values. You remember, fix the energy and fix the variance. And then you would like to know what is the computational time. Then it turns out that with matrix product state, this computational time scales like the exponentials of the inverse of the variance, right? And so that's something you can check. You can use a reference. And since delta is interesting when it's of the order of 1 over n, then you see that this problem for interesting problems scales exponentially with n. So this is why even in 1 dimension, this to use classical algorithms to solve these kind of problems would take an exponential time. Now, for the second problems, for problems at finite temperature, the most celebrated algorithm is called quantum Monte Carlo, the most celebrated classical algorithm. And this works very well for problems as long as there is no sign problem. So what happens is that the Monte Carlo algorithm, what it does is sample classical configurations. And then in order to sample, you have to be able to compute what is the probability of each configuration. And there are some problems for which this probability can be efficiently computed with a quantum computer. You have a configuration, and to compute what is the probability, you can compute it. So then you can know whether you have to take this configuration or not. However, there are some problems for which it's exponentially difficult to compute what is the probability of this configuration. And these are problems that are called, these are problems that are known or that are referred to as having the sign problem. And for them, this method takes an exponential time. So there are problems now for finite temperature that with quantum computers, and interesting problems have the sign problem, and it also requires exponential time. And so what what about with a quantum computer? Well, with a quantum computer, you see that the way that I put it, then since I took an arbitrary energy, I could have taken the energy to be the ground state energy, and then I'm back to the ground state problem, and I told you that this is QMA hard. So there will be some range of energies for sure, for which the problem will be difficult. However, it may happen that as you increase the temperature, all of a sudden there is some energy, there is an energy for which it's efficient with a quantum computer, but it's still difficult with a classical computer. And maybe you go on, and then at some other energy is difficult, is easy for a quantum computer, but also easy for a classical computer. So there may be some range of energies for which a quantum computer is more efficient. And this is indeed what happens. And the same thing for temperature. At 0 temperature, you're back in the ground state. So you put here 0, then this problem is QMA hard. So as you increase the temperature, it may well be that at some particular temperature, the quantum computer is efficient. And if you increase even more the temperature, then classical computers are efficient. So this is what we have been looking at. And those are these algorithms that I wanted to mention. And just to very fast tell you what is the idea. So the idea is you give me the energy for the first kind of problem. You give me the energy to prepare a product state, to prepare a very easy state with this energy. However, the variance will be very big. So that's not a good state. The second is to apply a spectral filter. So to apply to quantum circuit that actually makes this state narrow in variance until the desired value. And the third part consists in not computing the state, never preparing the state, but actually performing many measurements that avoid you even to prepare the state. So that's the trick behind this algorithm. Don't have time to explain it in detail, but nevertheless, so let me tell you what it achieves. So that's here. So this quantum algorithm, actually what it does is that prepares a product state, then evolves it for different times and measurements, and repeats this procedure many times, and at the end computes some expectation values just using a classical computer with all the data that you have. Then you put it in a classical computer, runs an algorithm, classical algorithm, and gets the result. And the computational time with this algorithm scales like n polynomial in n in 1 over delta and 1 over epsilon. And I told you before that the interesting part is when delta is of the order 1 over n. So you see that it scales polynomially with n. So there is an exponential speed up. This is not written here. There is one condition though, is that this energy should be large enough in such a way that there is state that can be efficiently prepared with that energy. And this is why it doesn't contradict any QMA hardness. But already you take typical problems, then you can see that you can solve problems with this quantum algorithm that you cannot solve efficiently with a classical computer. And this can run in analog quantum computers and this device. So all these procedures that I told you before, I mean, then can be done with, you have an analog quantum computer. You don't require a quantum computer, at least for some particular Hamiltonians. The other algorithm works for finite temperatures, and for finite temperatures, the idea, I mean, don't go to that. The idea is to what you do is that you're going to use classical Monte Carlo. So the Monte Carlo method that I told you before, you can use it. However, you use it in a classical computer, has the sign problem. And the reason, as I told you, is because whenever you want to compute this probability of a configuration, it takes an exponential time. Actually, what this quantum algorithm does is that it computes this probability efficiently with a polynomial time. So it allows you to run in a classical computer quantum Monte Carlo using a quantum computer as a subroutine to compute the things that are difficult for a classical computer. And so we have tested that with some models and so on. I don't want to tell you much about that. I had another part related to analog quantum simulators, very briefly. So the idea is that in analog quantum simulators, then, I mean, you don't have to run gates. They are existing already with many technologies. And they have some advantages and disadvantages with respect to quantum computers. The basic advantage from my point of view is that if you're interested in intensive quantities, so energy per particle, magnetization of particles, and so on, then the errors are not that bad, because the errors are only bad if you're looking at extensive quantities. I wanted to talk a little bit about that. But anyway, so this is the advantages, and maybe I just wanted to tell you a little bit about also some algorithms, and one that we are very proud of, that Javier, who is at ICFO, was the main person working on that, and that works for quantum chemistry. But nevertheless, so let me go to the summary. Okay, so we're talking about quantum simulation with quantum computers, analog and digital quantum computers, these devices. And so the goal of these systems would be maybe to solve specific problems, Hubbard models and things like that. But even more important would be to provide some understanding to this model. So I always say that imagine that you have now a quantum computer that can solve the Hubbard model, and then you say that this is the reason why you want to build this quantum computer. But it may well be that using some different techniques, for example, tensor networks, you can solve the Hubbard model. And so all of a sudden, if somebody solves the Hubbard model with tensor network, then what does it mean? That your quantum computer would not be useful? Not. Because it will allow you to explore many other things, that it's not only some specific model. So it would like you now to start tuning parameters, to investigate the new phenomena, to investigate it, to have some understanding of how things are working. And what I think that is most important, will allow you to benchmark theory. So at the moment, I mean, many people at ICFO, at MPQ, in TUM, in LMU, in many other places, the universities in Barcelona, are developing numerical methods to solve in classical computer many-body systems. And one of the drawbacks that we find is that there is no way of benchmarking. You have a model, you have a method, it gives you some results, so is it right or is wrong? You had one of these quantum simulators, then you could train these methods and then make them more efficient, and maybe at the end you don't use the quantum computers at all for quantum many-body systems, but just these classically trained systems. And the same thing could happen with machine learning. Okay, I can use machine learning, train with models and then use them to solve models. And so I think that with that, I would like to finish before showing a picture of the whole department at MPQ when we had our yearly retreat that this time happened at home with another platform. It was not this stage, but it was a different one, which each of us had an avatar. And so we had a lot of fun there. And I hope that you also have fun in your workshop here. So thank you for your attention.
Thank you very much.